I have prepared a practical example now to see how we can design a glass balustrade. So glass balustrade, all the times they are using laminated glass to ensure safety. And we will perform a ULS check, SLS check, and we'll go also through a failure scenario, which is mandatory. When one of the glass span fails and the other, through the steel railing, have to take the extra load. And we can also check the steel rail. So I will switch now to CI Engineer. And here we have these three models. We can work on a unique model. We can have construction stage model, or we can have different models. I wanted to keep things clear, from theoretical point of view. So this is why I copied this simple structure 3 times. So these are some glass panels. This is 1.1 meters, 2 meter long. And the glass panels are modeled as shell elements, and they have a thickness calculated. And I'll show you how I got to this 13.8 thickness. This is the deflection model. And when we go for the tension model, we'll see that there's something else is 15.4 millimeter, which will be kept also for the post-failure model. So we go to the load case. Something simple. I just inputted here the self weight, calculated automatically by the software, and a lateral push of 0.75 kilonewtons per meter that act on the steel railing. So this is actually a steel element, simulates the handrail, and it also has a structural load. So when this glass fails, this steel element needs to be strong enough in order to transfer the loads to ADHN panels. Now let's have a look on how things look inside the software. So after we model the geometry and place the loads, we can create combinations. There can be linear combinations and non-linear combinations. We need non-linear for the geometric analysis. So here, one thing I did in SIA was to activate the module called non-linearity and the module called geometrical non-linearity. And then the model is already calculated. And after you install the software, we'll get to that point, but you'll just have to install a software. It will create a new icon on your computer, which is called add-ons. And depending on the license that you have, you will see that module. So here are the modules presented. There's one missing today, the triple insulated glass, but it will appear in the final kit. And each module has 2D member data, through which we can add additional attributes and information in order to calculate the glass. And the check itself. The check only can be seen after the model has been calculated and we know the forces. So what I'm going to do now is go for 2D member data for laminated glass. I'll go here in this dotted points. And here we can select from the database different types of glass. If it's surface pre-stressed, I will leave a soda lime silicate glass. This is the most typical. These information usually are taken from the glass producer. So if we ask glass producer, he needs to give us all this information also regarding the process. The glass surface, if the glass is sandblasted or not, and if pre-stress has occurred, which kind of toughening it's done. And usually the glass is thermally toughened because, as I said, it gives a boost of up to 3 times the capacity of annealed glass. Then there will be the loads. Here we need to input the proportion of the loads because depending on the proportion of the loads, the K mode factor will be calculated. So when we input here the values, we calibrate the K modulus and it will affect the final capacity. And then for the deflection, there are different provisions to calculate the serviceability limit, and we need to specify the element type, and also we can input the element height. Why you have to input it? Because when we model glass, in this module at least, we will go with shell elements. We can start with linear elements, but in the end we'll transform everything into shells. Why we do that? Because as I stated before, we need to see what happens with the load concentrators. So with the stress concentrators, we need to see exactly how the connection occurs and where they are present, because those are the points where the structure would fail. And then there's the edges. This is a provision that actually reduces to 90% the capacity if we want to consider the fact that the edge has been treated. And most of the time, edge is treated because otherwise people can get cuts from it. We have seamed or polished edges. And then we get to the laminated. And here we input the load. This is just for the code. We need to keep this 0. We neglect the first layer. And we input here the thickness of the glass, so it can have as many layers as we want. So when we click, it will start to add more layers, but we will stick to 2 layers of 10 millimeters. And we can also choose the family of the interlayer type. So this is according to the European code. And when we choose the foil, or actually the producer of the laminated glass has to tell us which foil he used, this will influence the effective thickness. So what we choose here will influence the final effective thickness. I'll say save, OK. And what I did so far was to establish some 2D member data that I can add to different elements. So I can have a very complex model and have different thicknesses of glass. In this situation, I will keep things simple. So I just select everything and it will add this additional data. And now I will select these glass panes and go for laminated glass stress check, current, and I will do a refresh to see some results. So we have different results. So SIA will display graphical the results. Now we actually see the unity check, but we can check principal stresses. Because glass is a brittle material, all checks need to be using principal stresses. So sigma 1 and sigma 2 are the ones that are needed to be checked. So if we want to manually, we know the capacity and manually check, we'd go for sigma 1, sigma 2. And if we want to see the capacity, we go with this value, FEGD. And then I can go with unity check, because it will show me the ratio between the force and the capacity. So as long as I am under 1, I am safe. If I'm under 0.5, it's not that economical. So we see here the distribution, the influencing of the corners, and this is the unity check shown graphically. And we can send this to an engineering report, even as 3D PDF. And further, we want to see what is this 0.58. It's like a black box. We don't trust this. It's glass. We're afraid. We need to understand what does this value mean. So to get to that value, we have to make sure that in the output, we select detailed and we go with preview. And then we see here how the capacity is evaluated, the K modulus, which depends on the load. This is the information it gets from when I selected the glass. And for that, you can import the glass. So I already shared with you through email. With material, this is the database of the glass. I shared it with you. And if you want to add it to your new project, although I'll include it in the shared example, you can read it from here. So I promise I'll show you. This is how we read it. So when we define the new project, you just select other material and read it from this file from the database. In future version, it will be automatically included in SIA, but for now, this is the way it will work. So this will show me the capacity of the glass, and it will also show me transparent formulas on how we got here. It will also tell me what is the allowable deflection, and I can check on this secondary model the allowable deflection. I think it's 24 millimeters, and I can go with 3D displacement and check the displacement, and I see what are the values and from the SLS combination. And this is post-failure model where some of the glass has failed, so the middle pane is missing here. So we will also check what's happening here. So I will go to add-on and perform the check from SLU, ultimate limit state actually. So because of this lacking of intermediate panel, we have some stress concentrators here in the corners. So this can be prone to failure. And again, if we hit preview, we'll see exactly what it used to determine the capacity and how it compares to the unity check. And we can also have a look on what happens with the railing. So the steel part is actually part of the CA engineer. So if I go now to steel, I can also perform a detailed check of this bar to see how it behaves under the load combinations. SLU, and we will run. We see that this fails from a overall unity check. If I were to perform only a section check for it, maybe it will be okay. And also here it's the same principle as my glass module. If we go to preview, we'll see exactly what formulas have been used. So this is a brief, but we can go for a more detailed report, and we'll see exactly all parameters, buckling lengths, and so on. So what are the forces it's subjected to, and so on. So stress and section check and stability check, and this is just because we are inside the CI environment.